Hello everybody, this is Lucia Valbonesi from Cambium Networks, and today we will talk about Massive MU-MIMO. Why is Massive MU-MIMO such an important technology? It is because it addresses one of the main challenges of today's networks, which is increased demand. Increased demand is due typically, especially to internet video, because internet video has been increasing year over year. Sorry, I think we are out of the presentation mode here. Okay, there you go. It's been increasing year over year, and it is expected to keep increasing over time. From an access point of view, the increased demand can be seen in two different ways. One way is having a denser sector, meaning more subscribers per sector. Another way is to have the same number of subscribers per sector, but now each subscriber is requiring a higher throughput. Either way, the access point needs to be able to handle a higher capacity. It's also important to future-proof the network, meaning to design a network today which is cost-effective, but it also thought out for the increased demand of the future. Because we expect the capacity to increase over time, we need to make sure that the network can handle not just today's demands, but also what we expect will happen in a few years from now. How did we get to Massive MU-MIMO? Massive MU-MIMO is composed of three concepts: MIMO, Massive, and Multi-User. Let's look at each one of these, starting from MIMO. MIMO means multiple input, multiple output, which means multiple antennas at the transmitter and at the receiver. This is the technology used to multiply the capacity of the wireless connection without requiring additional spectrum. The portion that we don't require additional spectrum is very important because the spectrum is scarce and not readily available in many areas. If we can use the same amount of spectrum but send higher throughput, this is obviously more efficient. The simplest communication system has one transmitter and one receiver. We can think of a vertically polarized antenna at the transmitter and a vertically polarized antenna at the receiver. We can send one data stream through this communication channel. Now imagine that we add an horizontally polarized antenna both at the transmitter and at the receiver. Now we have two antennas at the transmitter and two antennas at the receiver. So we have a 2x2 system where the 2 and 2 stand for the number of antennas at the transmitter and the receiver. We can use the two antennas in two different ways. We can decide to transmit the same data stream through both antennas and use a combining gain at the receiver in order to increase the sensitivity of the link, essentially to make the link more robust. Or we can decide to send two separate data streams, therefore doubling the throughput, but in this case, we do not make the communication link more robust. This because there is no combining gain. This second application is what is typically used because it is desirable to send as much data as possible through the wireless channel. So with the two antennas at the transmitter and two at the receiver, with the 2x2 system, we can double the system capacity. Of course, we can go beyond the 2x2. We could have a 3x3 system, we could have a 4x4 system, we could even have an asymmetric system with a different number of antennas at the transmitter and the receiver. For example, we could have a 4x2 system with 4 transmit antennas and 2 receive antennas. The more antennas we had, the higher the capacity is, but also the complexity of the system becomes higher and higher because we need to be able to separate all these data streams. So at one point, we have diminishing returns because the complexity becomes very high unless we use some smarter way of using all these antennas. If we have a system that goes beyond 8x8, then we talk about massive. This is what the term massive means. It means that we have more than 8 transmitters and 8 receivers. The MIMO technology increases the capacity between two wireless nodes. So the benefits are seen one subscriber at a time. So it's important to understand that the subscriber needs to have the same capabilities than the access point. In this case, this means the same number of antennas. For example, let's assume we have a sector where the access point is 2 by 2, and this access point communicates with the mixed population of subscribers, where some are 2 by 2 and some are 1 by 1, meaning that some have 2 receive antennas and some have only 1. The access point can send 2 data streams to the subscribers that have 2 antennas, but only 1 data stream to the subscribers that have 1 antenna. So if the subscriber doesn't match the capability of the access point, then there is no benefit. The last piece in the Massive MU-MIMO terminology is the multi-user portion. The MU-MIMO allows the access point to communicate to several subscribers simultaneously. Again, this happens in the same spectrum, and multiple data streams are sent to multiple users, therefore making the communication even more efficient. Massive MU-MIMO is based on spatial multiplexing. What is spatial multiplexing? It is making concurrent transmissions possible in the same wireless spectrum by using physically separated radio beams. The key here is beamforming, meaning the ability of creating a narrow beam by tuning the antenna elements at the access point. In the plots here, we see the difference between the pattern of an antenna, a typical sector antenna to the left, and a beamforming pattern in the middle. A typical sector antenna covers the entire sector, which has a beam width of typically 60 degrees, 90 degrees, or 120 degrees. All the subscribers in the sector receive the same signal, regardless if they are intended recipient of the signal or not. And there are other mechanisms for the subscribers to understand if the transmission is destined to them or not. In the beamforming method, the beam is much narrower and it's pointing towards the subscriber that is the intended recipient of the transmission. Now, because this beam is much narrower, it's possible to create multiple of these beams. And in the figure here to the right, we see 7 beams facing 7 different subscribers. This is again possible by tuning the antennas so that the peak of the beam is in the direction that we want. In this picture, it's obvious that the peak of the beam faces the location of the subscriber. But what's also important to understand is that each beam also has nulls in the direction of the other subscribers. This minimizes the interference between the data streams. So for example, if you look at the data that has to be sent to subscriber number 3, we see that the third beam has the peak towards subscriber number 3, but it also has nulls in the direction of subscribers 1, 2, 4, 5, 6, and 7. Again, this is done to minimize the interference received by the other subscribers coming from the data stream which is intended for subscriber number 3. How can the access point tune its antennas to create these patterns in these specific directions? This is done by using the channel state information, which is available at the access point through the sounding process. Sounding is done exactly for collecting all this information on the channel between the access point and each of the subscribers. The access point is sending a sounding symbol, which is a known signal, and then each of the subscribers will report back how they received this signal. And there are mechanisms to make sure that the feedback is compressed so that not to use a lot of the uplink resources. Now, the access point has information on what the transmitted signal was, what the sounding symbol was, and also what each of the subscribers is feeding back in terms of how they received the symbol. And by having the transmitted symbol and the received symbol, the access point knows what the channel looks like in between the access point and each of the subscribers. So this is what allows the access point to know where the subscribers are and where to point the beam. The PMP450M access point is using Massive MU-MIMO technology. This is an outdoor point-to-multipoint access point which has 14 antennas. There are 7 vertically polarized antennas and 7 horizontally polarized antennas, which means that the access point can handle up to 14 streams, and these streams can be sent to up to 7 subscribers. The subscribers operate in 2x2 mode, meaning that the subscribers only have 2 antennas, one vertically polarized and one horizontally polarized, and can receive 2 streams. So the subscribers do not need to match the capabilities of the access point. The subscriber is a much simpler device, it's only 2x2, while all the complexity is on the access point, which is 14x14. The PMP450M access point can operate in several operating modes, in the downlink direction and in the uplink direction. Let's look at each one of them. In the downlink direction, the first mode is the downlink sector mode. This is used to transmit broadcast data to all subscribers or unicast data to subscribers that did not provide channel state information. This mode is functionally equivalent to a traditional 2x2 access point, meaning that it illuminates the whole sector and the signal is received by all the subscribers. This is used if the data is intended to all the subscribers, like broadcast data, or we said if the subscriber did not provide channel state information. If the subscriber didn't complete the sounding process, for example, this is an older subscriber that does not support sounding, then the access point doesn't know where the subscriber is and cannot point the beam in the direction of the subscriber. So the only solution is to, again, broadcast the data, meaning sending the data in the whole sector to make sure that the subscriber can receive it. The second mode is downlink beamforming mode. This is used to send data to one subscriber that provided channel state information. Now, because this subscriber completed the sounding process, the access point knows where the subscriber is and can point the beam towards the location of this subscriber. And the third mode is the downlink MU-MIMO mode, which is a transmission to multiple subscribers that provided channel state information. This is what we saw before when we created multiple beams in multiple directions. And of course, these subscribers need to have completed sounding because the access point needs to know in which direction to point the multiple beams. In the uplink direction, the modes are similar. The first one is the uplink beamforming mode. This is used to receive data from one subscriber that provided channel state information. Again, the subscriber needs to have completed sounding for the access point to know where the subscriber is, so that it can point the received beam in the direction of that subscriber. The uplink MU-MIMO mode is used to receive from multiple subscribers that provided channel state information, meaning that the access point will generate multiple beams to receive from multiple subscribers. And again, it needs to know the channel between the access point and these subscribers. Both these modes, the beamforming mode and the MU-MIMO mode, are used only for scheduled transmissions, meaning that the access point knows which subscriber is sending at what time, and it can form the beam in the direction of that subscriber. However, there are also some transmissions that are not scheduled. For example, when a subscriber is first registering, it needs to send a registration request, or the subscriber is sending a bandwidth request when it has data to send. These transmissions are not scheduled, so the access point doesn't know which direction the transmission is coming from. For this reason, the access point needs to be able to receive from all the directions. And this mode is called multiple fixed uplink beamforming mode, because the access point is creating multiple overlapping beams to make sure that it can receive from all the directions in the sector. All these operating modes are used within each one of the TDD frames by the PMP450M access point. Here we see the different types of symbols that are transmitted in the downlink direction and in the uplink direction in every frame. We'll walk through each one of them to see which mode is used for which type of symbol. This happens every frame, and from symbol to symbol, the access point can switch from one operating mode to another without needing any guard band. So we can have one operating mode, one symbol in one operating mode and the next symbol in another operating mode without needing any idle time to switch from one mode to the other. Let's walk through all these types of symbols in a frame. The first type of symbol in a frame is control symbols. These are symbols that are sent in broadcast mode because they need to be received by all the subscribers. These are the AGC symbol that's used by the subscribers to set the gain, the preamble that's used by the subscribers to align the frame in frequency and in time, the beacon, which contains configuration parameters of the sector, and the uplink map, which contains the schedule that indicates to each subscriber when they can transmit during the uplink portion of the frame. Because this information has to be received by all the subscribers, this is sent in sector mode. Next is sounding. We said that this is the process that's used to collect the channel state information from each of the subscribers. The channel state information is used for several purposes. First of all, to determine if the subscriber is eligible for a beamforming and MU-MIMO transmission. It's important that the access point can understand the exact direction of the subscriber. Let's assume we have a scenario where the subscriber is close to an object that creates a strong reflection. Now, the access point is receiving the direct signal from the subscriber, but also the strong reflection. So it's difficult for the access point to understand which is the right direction towards that user and where to point the beam. So in this scenario, the subscriber could be marked as ineligible for beamforming and MU-MIMO. But if there is a clear line of sight, then the subscriber will be eligible for beamforming and MU-MIMO transmissions. And this is determined through the sounding process when the access point has the channel state information from that subscriber. The channel state information is used to calculate the physical layer weights for the beamforming communication. These physical layer weights are the values, the parameters that are used to tune the antennas in order to steer the beam in a specific direction towards the user when we communicate in beamforming mode. Also, the channel state information is used to establish groups of SMs in MU-MIMO mode. When MU-MIMO mode is used, the access point is communicating to multiple subscribers at the same time. The way the access point picks the subscribers to be part of a group, that depends on their channel state information. Also, the channel state information is used to calculate the physical layer weight for the MU-MIMO transmission. Again, these are the parameters that are used to tune the antenna so that we can form these multiple beams in multiple directions. Here we see one example of the sounding symbol where the two colors indicate that some subcarriers sound the vertical antenna and some subcarriers sound the horizontal antenna. Of course, we need to sound both at the subscriber to make sure we have the full picture on how the signal is received at the subscriber so that the access point knows how to form these beams. The next is the transmission in the downlink direction in a unicast mode. This is data that is going to subscribers one by one and is not grouped, either because we cannot group or because we don't want to group. So depending on the two cases, we can either transmit in sector mode or in beamforming mode, depending on the subscribers. If the subscriber did not provide the channel state information, then we need to operate in sector mode. If the subscriber did provide the channel state information, then we can operate in beamforming mode. Still, we use this beamforming mode instead of MU-MIMO because we do not want to group this type of information. For example, the downlink X, these are the acknowledgements to the transmissions received in the previous uplink direction, or for example, high priority traffic. Typical example is a VoIP packet. These packets are short and they are sensitive to latency. So it's better off to send these packets quickly and not wait for them to be part of a group. Also, when we form a group, we want to make sure the subscribers we select have a large data to transmit, because we don't want to form a group and then having one of the subscribers to only receive a short packet and then keep transmitting only to the other subscribers when one is done with its transmission. This is why to form the group, it's preferable to have a larger amount of data, while the high priority data is typically composed of short transmissions. So these short transmissions are better off being sent quickly one by one before we go on and form the group. The next one is the MU-MIMO transmission, which is the group. And in this case, we form multiple beams in the direction of the multiple subscribers. In order to be eligible for MU-MIMO transmission, a subscriber needs to have a valid spatial frequency. This is what we refer to, basically you can think of this as being correlated to the azimuth. This gives the information of where physically the subscriber is in the sector. And of course, it's important to know in which direction to point the beam. The scheduler, the downlink scheduler at the access point needs to go through several decisions to make sure it picks the best subscribers to be part of the group. First of all, it needs to look at subscribers that have pending data. This may be obvious, but if the subscriber doesn't have any data to receive, then obviously it will not be picked to be part of the group. The subscriber needs to be MU-MIMO eligible, so it needs to have a valid spatial frequency, which means it completed the sounding process. And we need to have the spatial separation between two subscribers to be at least 6 degrees. This is because if the subscribers are too close to each other in azimuth, then the beams overlap too much and it's not possible at the receiver to separate the beams. So there has to be a minimum physical separation between the devices in order to be able to be part of the same group. The downlink scheduler also has to consider many other parameters. Any quality of service parameter also plays a role here. For example, if some data channels are configured with CIR, or committed information rate, then those data channels need to be scheduled before the data channels that met their committed information rate, or that were not scheduled with committed information, that were not configured with committed information rate. Also, the PMP450M supports up to 4 quality of service levels, and for each level, the scheduler needs to look at the data channels that met or did not meet the committed information rate. So the scheduler looks at all the quality of service parameters to make sure it picks the data channels that need to be scheduled first. And also it looks at the physical deployment of the subscribers to check which subscribers can be scheduled together. And based on all of this, it selects the best group of subscribers to be part of this MU-MIMO transmission. And the goal is to maximize the sector throughput, so to pick the subscribers that will transfer the largest amount of data. If the MU-MIMO group that we formed that did not use all the symbols in the downlink direction, and there are any symbols left, then these symbols are not left unused. Obviously, we want to use all the resources, and they are used in a unicast mode again. So like before, we can use either sector mode or beamforming mode, depending on which subscriber we are communicating with. The subscribers that did not provide channel state information are communicated to in sector mode, and the subscribers that did provide the channel state information are communicated with in beamforming mode. So this concludes the downlink portion of the frame. At this point, the uplink portion starts. And the first mode in the uplink direction is the uplink unicast. In the uplink unicast, the access point is receiving from one subscriber at a time, forming a beam in the direction of that subscriber. Because all the antennas work together to receive from one specific direction, the sensitivity of the access point in the uplink direction is much better. If we compare the sensitivity of the PMP450M access point to the sensitivity of the PMP450, which is a traditional 2x2 access point, we see that the sensitivity is up to 12 dB better because of this capability of focusing all the energy in one specific direction. The next mode is the MU-MIMO mode in the uplink direction. In this case, the access point is forming multiple beams towards multiple subscribers, and these subscribers can transmit at the same time. This mode is similar to the downlink mode, the downlink MU-MIMO mode, meaning that it has many of the same challenges and requirements. First of all, the subscribers have to have a valid spatial frequency to be considered eligible for uplink MU-MIMO transmission. Like for the downlink direction, we need to make sure the subscriber has completed the sounding process, so the access point knows where the subscriber is and can point the beam in that direction. Also, we want to make sure the subscriber is not operating at the lowest possible modulation, but at least one level up, which is a QPSK dual stream. The reason is that we want to make sure the link is still stable, even if there is some residual interference from the transmissions of the other subscribers. The uplink MU-MIMO scheduler works very similarly to the downlink MU-MIMO scheduler. Again, it will look only at subscribers that have pending data, meaning the ones that sent bandwidth requests, only subscribers that are MU-MIMO eligible, and again, subscribers that have a minimum separation physically in azimuth between them so that they can be part of the same group. The uplink MU-MIMO feature is not available in standards like 802.11 or LTE, but it will be available in the PMP450M access point later this year. Both of these modes, the uplink unicast and the MU-MIMO receive mode, are used for scheduled transmissions where the access point knows which subscriber is transmitting. The last mode is the one used for the contention slots. Contention slots are the ones that are left free for all, meaning with a random access procedure, so that the subscribers that are not scheduled have the opportunity of sending a bandwidth request, for example, or a registration request. The access point is forming 7 mini sectors where we see these 7 overlapping beams that cover the whole sector. In a frame, in a PMP frame, we have 2 types of contention slots. There is a fixed number, which is always available, and there is a variable number, which is equal to the number of symbols that were not scheduled. So any uplink symbol that is not scheduled is not wasted, and it goes into the pool of the symbols that can be used for random access. What is important to understand here is that because we have these 7 mini sectors, each of these mini sectors is connected to one of the 7 demodulators in the access point. So if we have 7 concurrent transmissions from 7 subscribers that happen to be each in one of the mini sectors, it is possible for the access point to receive all the 7 transmissions without any collision and without interference between them. And this is important because it's different from the traditional 2x2 access point. In a traditional 2x2 access point case, if 2 subscribers happen to select the same symbol for random access transmission, there will be a collision at the receiver at the access point, and most likely both transmissions will be lost. So if 2 subscribers send a bandwidth request, but they don't receive an allocation because there was a collision, then they both go into a random backup mechanism where they pick randomly another symbol, and the mechanism is made so that it's unlikely that the 2 subscribers will pick the same symbol again. The more collisions there are, the wider the window is among which to pick the random symbol, so the latency of the system is affected. That's why we want to make sure we do not have a large number of collisions at the access point. With the PMP450M, because of these 7 mini sectors, if 2 subscribers that happen to select the same symbol are in different mini sectors, both transmissions will be correctly received at the access point. Again, this is very important because now we do not have a collision and we do not have to start this random backup mechanism. So the only way where we can have a collision is if 2 subscribers pick the same symbol and they also are in the same mini sector. Now, all of these that we have discussed happen frame by frame. A frame is 2.5 milliseconds long or 5 milliseconds long. And each frame, we said, has a downlink direction and an uplink direction. Each direction is composed of a number of symbols, and each symbol can use any of these operating modes. And you can see here how quickly the access point can switch from one operating mode to another operating mode. We said every symbol, there is no guard time between the operating modes. And this happens 400 times per second with a 2.5 millisecond frame. So you can see how efficient the system is, because in every symbol, the access point will select the best operating mode for that specific transmission. Well, the main advantage of the PMP450M access point is clearly the higher sector throughput because of the massive MU-MIMO feature. In a 20 megahertz channel, the PMP450M can have up to 800 megabits per second if you have MU-MIMO both in the downlink and in the uplink direction. This is a spectral efficiency of up to 40 bits per second per hertz in one individual sector. And if you deploy 4 sectors in a site with an AB-AB frequency reuse, meaning that the 2 back-to-back sectors use the same frequency, then the spectral efficiency per site is up to 80 bits per second per hertz. So obviously this is a great advantage because the higher sector throughput is the first thing we are looking for in an access point. The reason why we can have such a good throughput is because we can group up to 7 subscribers at the same time. However, these figures are not equal to 7 times the throughput that you would normally have with a traditional 2x2 access point like the PMP450 or 450i. The expected improvement when using a 450 MAP is in the range of 3 to 4 times. So why don't we get that 7x multiplier? Well, there are some practical limitations. First of all, when a subscriber operates in grouped mode, it is possible that it operates at a lower modulation compared to when it's ungrouped. For example, let's assume the access point is talking to a subscriber in ungrouped mode, and the subscriber is operating at 64 QAM modulation. When the subscriber is operating in group mode, there is always some residual interference from the transmissions to the other subscribers, and it is possible that this subscriber operates in 16 QAM modulation. So there is a reduction in the modulation to this specific subscriber. However, the overall throughput is still higher because the access point is communicating with 3, 4, 5, 6, up to 7 subscribers at the same time. So the overall amount of data that's transferred in the same amount of time is higher. Another consideration is that only the lower priority traffic is grouped. We talked about this. If we have a high priority traffic like void packets that are short, we want to send them quickly in beamforming mode, one by one, without having them part of a group. One of the main reasons is that we want the group to be formed by subscribers that have a large amount of data to transfer. Imagine, for example, we are communicating with 3 subscribers, where 2 have a lot of data to transfer, and the third one only has a short void packet. So we form a group of 3, we start sending the data, but one of the 3 has a short communication while the others keep going. This is not the most efficient way of forming a group. We are better off selecting another subscriber that has a large amount of data to send so that we can keep using the symbols in the group to send more data. So if a sector has a large volume of short packets or void packets, high priority packets, that's something to take into account because that will not be grouped. So we're not part of this expected improvement. Another consideration is that the subscribers need to have sufficient spacing in azimuth. We talked about the subscribers having a minimum separation among them for them to be groupable. Here we see some examples of sectors that are expected to have a better or worse grouping capability. In the plot to the left, we see that all the subscribers are grouped together physically in almost the same location. So it's hard in this case to find a lot of subscribers to be part of the same group. Similarly, in the second example, the one in the middle, we see that the subscribers are spread wider, but they are not uniform. There are no subscribers in the middle of the sector. This could happen, for example, if there is a river or a hill or any obstacle that prevents subscribers to be installed in a certain portion of the sector. So the subscribers on one side of the sectors are groupable well with the other subscribers on the other side, but it's difficult to form groups with a large number of subscribers because there is nobody in the middle to be grouped with. The example to the right is the best because the subscribers are more evenly spread in the sector, and now it is more likely that we will find the more subscribers to be grouped together. Finally, subscribers can only be grouped if they have traffic. Again, this may be obvious, but if you don't have a lot of traffic going through your access point, then there is no opportunity for MU-MIMO to work, and you will not have any improvement over a traditional 2x2 access point. If the traffic is so little that the subscribers generate traffic not at the same time, there is never going to be traffic to group, and the capacity of the access point is the same as a traditional 2x2 access point. But once you start having a lot of traffic, now the queues become more full and you have more opportunities to group. That's when the MU-MIMO functionality kicks in, and when the 450M access point will show the benefits of the higher throughput. The PMP450M also has many other advantages besides the obvious higher throughput advantage due to the massive MU-MIMO feature. Another advantage is given by the beamforming feature, namely by the beamforming array gain. This is a gain that's given by the fact that there are multiple antennas in the access point, and it's present both in the downlink direction and in the uplink direction. In the downlink direction, we have to distinguish between two cases, between regions that are EIRP limited and regions that are not EIRP limited. Traditionally, the EIRP is seen as the sum of the transmit power and the antenna gain. But if we have multiple antennas at the access point, we also have a third term, which is the array gain. So the EIRP is going to be the sum of three terms: the transmit power, the antenna gain, and the array gain. Now, let's assume we have an access point which in sector mode has the sum of the transmit power and antenna gain. Here there is no array gain in sector mode, which already meets the EIRP limit of the region. If we switch from sector mode to beamforming mode, and now we also have the array gain on top of it, we cannot exceed the EIRP limit. If you already are at the limit, we cannot add the array gain on top of it. So we need to lower the transmit power so that the sum of the three numbers is still going to give us the EIRP limit. In this case, then there is no advantage in terms of link budget because the EIRP is the same, the link budget is not increased. However, there is still an advantage that we are operating in the access point at the lower power, which means there is going to be less distortion because the access point operates in a more linear region, and this increases the probability of the access point using a higher modulation. Different story is if the region is not EIRP limited. In these cases, if you're already reaching your EIRP limit or the maximum that the radio can do in sector mode with the sum of the transmit power and the antenna gain, when you switch to beamforming mode, now you're adding the array gain on top of it. So this goes on top of your link budget, and now a higher link budget means increased range and higher average modulation. In the uplink direction, there is no distinction because obviously there is no EIRP limitation in receiving. So the array gain is added to the sensitivity of the device, which means we have an increased link budget, which means we have a higher average modulation, and at the end of the day, this translates into higher sector throughput. With beamforming, the array gain is one of the advantages, but there is another one, which is reduced interference. And this is an advantage both in the downlink and in the uplink direction. Because with beamforming, we are forming a narrow beam in one specific direction, in the downlink direction, we only create interference in that narrow path, in that narrow beam towards the subscriber. And in the uplink direction, we are only receiving possible interferers from the same narrow direction, while all the other interferers are rejected if they are outside the narrow beam. And we see in these plots an example of a comparison of uplink performance between a traditional sector mode and beamforming mode. In the plot to the left, we see that the access point is communicating with multiple subscribers at different modulation levels. The 4 shades of blue represents the different modulation levels: 256 QAM, 64 QAM, 16 QAM, and QPSK. So the 3 subscribers that are farthest from the access point are communicating in QPSK mode. Now, if we use beamforming, now we can squeeze the beam in the direction of the one intended subscriber. We have an array gain on top of what the sensitivity was before, and we see that that subscriber at the edge of the sector can now communicate in 16 QAM mode, which means that we have doubled the throughput of that subscriber. So the first advantage is an increased throughput, but we also talked about reduced interference. Let's imagine that the red device is an interfering device using the same frequency. In sector mode, this device is received at the access point at the same time where the access point is receiving the desired signal from the subscribers in the sector. So the presence of this interference will corrupt the reception at the access point and possibly force the subscribers to use a lower modulation level if the interferer is always present. In a beamforming mode, because we are forming a beam in just one specific direction, if the interferer is outside this direction, then its signal is rejected at the access point receiver, and this interferer is not really affecting the reception at the access point, which does not degrade the modulation that the subscriber can use in the uplink direction. So there are 2 benefits here. On average, we can use a higher modulation because of the array gain. And also, if you can reject the interferer, then we do not have any degradation at the receiver. The PMP for 50M access point has a very sophisticated antenna, which can be used for Massive MU-MIMO, for beamforming, like we discussed. But there are other advantages here that are also important, even maybe less commonly discussed. Here we'll talk about 2 of these: a built-in 2-degree electrical down tilt and null filling. Let's start with the down tilt. Down tilting is a common practice because typically the access point is installed at higher elevations than the subscribers. So if we down tilt the device towards the subscribers, we have more subscribers closer to the peak of beam of the antenna. And also the access point is creating less interference to neighboring sectors that are reusing the same frequency. This down tilting can be done either mechanically or electrically. Mechanically means that we physically tilt down the device. One problem here, though, is that the angle that we tilt this device it is correct only at both sides, meaning that the tilting angle is what we want right in front of the device. But at the edge of the sector, meaning on the 2 sides of the sector, the tilting angle is lower. So the benefits that we have with this tilting angle peaks in front of the antenna, but is lower on the sides of the antenna. If we perform the same down tilt electrically, because now we can control what the antennas do, then we have the same tilting angle uniformly across the sector, which means that the positive effect is the same across the sector, not just in front of the antenna. The second property is null filling. A typical access point antenna without null filling may have multiple deep nulls when you move closer to the access point. These are locations that are close to the access point where the signal is greatly attenuated at the subscriber receiver. This means that the subscribers will operate at much lower modulation level, or it could even lose connection if the null is very deep. If this antenna is designed for mobile applications, this is typically not a big problem because being in a deep null location is temporary. Because in a mobile application, the subscribers will move. If they happen to be in a deep null, they will lose connection or operate at lower modulation. But as they move away from the null, then they can restore the signal quality they had before. However, in fixed applications, clearly the subscriber is not moving. So if the subscriber is installed in a deep null, it will always operate in that degraded situation. And obviously, we don't want that to happen. So having null filling in the antenna is very important because we want to avoid these locations that will have a degraded experience. Now, both of these two properties, the down tilt and the null filling, seem to benefit subscribers in specific locations. We said the first one was at the side of the sector, and the second one was in locations that are very close to the access point. The truth is that everybody benefits from these improvements in the antenna design because these subscribers in these locations that have a better experience, they can now transfer data at the higher modulation, which means that the access point is spending less time communicating with these devices and can move on quickly to other devices. All the devices in the sector experience a better throughput and the whole sector capacity is increased. Let's conclude today's presentation talking about the two versions that are available for the PMP450M. There is a full version and a limited version. The full version has all the functionalities we discussed today, including MU-MIMO. The limited version does not have the MU-MIMO functionality in the downlink and the uplink direction. If you have a limited version, you can apply a software key and make this device a full version. The limited version, though, still benefits from all the other characteristics we talked about today, like the beamforming, the interference reduction, and also it is able of handling higher packet processing, like PPS, compared to traditional 2x2 access points. Why would you want to consider a limited version? Well, there are many cases where you start off with a deployment where the number of subscribers is small, and the higher cost of the full version PMP450M may not be justifiable by the small number of subscribers that you have today in the sector. Also, if the number of subscribers is small, then you don't expect a lot of traffic, which means that the MU-MIMO functionality will not operate in the access point, so it's not really needed. But as you add more and more subscribers in the sector, or the subscribers become more active over time, now the access point needs to be able to handle higher traffic. At this point is when the MU-MIMO functionality becomes beneficial, and you can unlock this functionality by applying the software key to the limited version to make this a full version. So this is what we were talking about at the beginning of the presentation when we talked about future-proofing the network. We want to be able to design a sector today for today's demands, but also make sure that we are ready for tomorrow's demands, in this case by unlocking the MU-MIMO functionality, so that we don't need to have any hardware change, but with a simple software key, we can enable the higher throughput that would be necessary a few years down the line. Thank you, everybody, for participating in this presentation today. If you have any questions, you can post them on the Cambium community, and we will send you the